Okay, so we got to look at a special situation. So here we got two reactions. Oops, sorry, I should back that up one. Nope, back it up. Cool. So here's what we got. We're looking at two reactions that both involve the same particles. Here we've got our hydrogen, dihydrogen monosulfide, or sulfuric acid, if you will. No, hydrosulfuric acid. It is an acid. It's reacting with this water to make our hydronium and our conjugate base. But theoretically, this conjugate base could react with some waters. Water could be the acid. It could get its hydrogen back to form our hydroxide. So this first reaction here is written as an acid reaction. We're forming hydronium. That's why it's got a Ka. And this Ka tells us how strong this species is as an acid. In the second reaction here, we're looking at, well, how good is this hydrogen sulfide ion as a base? So Kb, we're forming hydroxide, making OH minus. So here's our base reaction. If we were to do kind of the sum or the total reaction here, something interesting actually occurs. Because really what we're doing is we're comparing, I'm going to disappear for just a second here. We're comparing essentially this acid and its conjugate. These are the two particles that we're interested in. Now, if we compare them together, if we put them together, we actually try to get our overall reaction here. Well, the HS minus is an intermediate. Our H2S cancels out, and essentially we end up with H2O plus H2O makes, well, looks like H3O plus and OH minus. If you were to write the K for that, well, that's KW. It's H3O plus times the OH minus, which is a constant. Oh, cool. Well, that means that if we're going to combine these two equations, if we're going to combine these two equations, this would have a Ka, right? This would have a Kb. When we combine equations like this, we actually would multiply those together. We multiply those values together, which brings us to an interesting mathematical relationship when we're looking at an acid and its conjugate. We multiply our equilibrium. We would actually find that those cancel out. We saw this. We end up getting right back to our Kw expression. And if these two things are the same as our Kw expression, that means we can actually write a relationship where Ka times Kb equals Kw. Ooh, that's nice. That means two very important pieces. That if we know a Ka, we can solve for a Kb, or vice versa, because Kw is constant. It is 1 times 10 to the negative 14th. We know this. We also now have a way to think about our strength of our acid and our base, because Kw is constant. That means if the acid is stronger, if Ka is bigger, then the conjugate base would have to be less, or a weaker conjugate base. There's a direct relationship between our acid and our conjugate. And this actually shows up when we start to look at some values. So for example, we think about our strong acids, our really strong acids. Our strong acids have very, very weak bases. They essentially don't act as bases at all. For example, the conjugate of hydronium is water, which we know to be neutral. And so vice versa, if you had a strong base, its conjugate is very, very weak. And so there's this direct relationship between the two when we start to compare their acid and base strengths, because they have to equal, when we multiply them together, their Ka times Kb have to equal a static or constant value, that Kw. Cool, real quick, just because we mentioned a couple times, I want to kind of bring the relationship back around. This is a little bit of a weird video. We're hitting a couple different topics in here. I also want to talk about Ka a little bit more as well. Ka, again, is just a number. It's an equilibrium. It tells us how strong is our acid. The bigger the Ka, the more acidic, right? The larger the Ka, the more products that form. More products, that means more hydronium in solution, more acidic. The bigger the Ka, the more acidic our solution, the stronger the acid. There is a tool, just like we have for our hydronium calculations, we can solve for what's called a pKa. And the relationship is a lot like our pH. If you have a lot of H+, your pH is low, right? The lower on the pH scale, the more acidic, right? Same thing for our Ka. The bigger the Ka, the lower the pKa. As Ka decreases, pKa increases, or vice versa. As Ka increases, pKa would decrease. That's that logarithmic scale again. If you remember, to go from this value of Ka to pKa, we take the negative log of this. It's just a logarithmic scale. As Ka gets bigger, we have a stronger acid, acidity increases, and so we would say the pH decreases. There's a lot of different questions that can be asked then relating these couple things together, but if we have good functional understanding of them, okay, strong acid means it's going to be a big Ka, means it's going to be a little pKa and a little pH. And so think about how those relationships all start to tie together. It's going to be helpful as we're thinking about our different pieces. Cool. Also want to mention real quickly this idea of polyprotic acids. Polyprotic, poly means many, protic, protons. Polyprotic acids are acids that are capable of donating more than one proton. As a result, it gets a little more complicated when we start to do the math for these. We're going to do one together and we get back together. I just want to introduce the terms and the ideas, and then we're going to run a big old crunchy number for this one. What this means is we actually have to account for all of the H's, the first H and the second H, that start to come off. Examples of this would be like sulfuric acid, H2SO4, phosphoric acid, H3PO4. These have multiple H's. As a result, they come off at different degrees of reactivity. As a result, they have multiple Kas. They have what's called a Ka1 for the first H, a Ka2 for the second H, and vice, and so on and so on and so on. For most of our polyprotic acids, after you lose the first H, it gets way harder to lose the second H. It becomes a much weaker acid after the first H has been lost. It's usually on a magnitude of 1,000 to 1,000,000,000 times harder to try to get that second proton off. I said 1,000,000,000. It's a million, excuse me. 10 to the 4th, 10 to the 6th, that's a million. And so after the first H leaves, now you got this negative ion left. It's even harder to get the second positive proton to leave. And so a couple examples here. So here's our phosphoric acid. Here we're losing our first H to form kind of this conjugate base. This would have a Ka1. You'll notice there's a value. This is still a weak acid. But this H2PO4 species could lose another H to another water in our beaker. If that happens, we end up forming our second conjugate. Notice that we've lost another H. Here's our acid, conjugate base, water forming conjugate acid. And you'll notice that your Ka drops significantly. It's a lot harder to get that second hydrogen off. As a result, the Ka2 is way smaller, right? Power in the magnitude of 10 to the 5th in this instance. And again, we could have this third H try to come off to form just the phosphate ion in solution. When that happens, it's 10 to the negative 13. And so as we lose H's, we see a decrease in acid reactivity. It becomes less and less likely, which makes sense. We said this acid, this phosphoric acid, formed a conjugate base. It's more base-like now. Well, could give another H off and become even more basic or even weaker of an acid. Oh, there's that Ka-Kw interplay again. Essentially what this means is if you had multiple H's though, you would have to have multiple Rice tables. You'd solve for the H both times, and then you're going to add them together. We're going to look at an example when we come on back, but it's good to get some of the vocab here, get the notes that we need so that when we come back, we can start cranking on that math together to make sure that we're feeling solid as we're moving forward. Cool. Should you have questions or anything on video, please jot it down. I'll be starting questions coming off the video when I see you again in class.